Hello again, everyone. We can continue with our doctoral degree category, and we have 6 presenters. As we know, the doctoral degree is much more complicated, and I hope presenters will describe their thesis and research quite good. So we could start with Antonio Tupek.
I am here.
Yes, very good. And he's from Zagreb University from Croatia. And yes, you're ready, yes?
Yeah, I'm ready.
Very good.
Thank you, Mr. Cleve, for the short introduction. I am very glad to have the opportunity to talk to you about my PhD research in the field of global navigation satellite systems, particularly antenna calibration. So to jump right into it, positioning by GNSS is definitely an important tool of modern society. But when high accuracy positioning applications down on the millimeter and centimeter levels are considered, quite a long list of error sources must be in appropriate manner accounted for. One of those error sources is the phase center model of the receiver antenna. Basically, and it all comes down to physics, the signal reception point within the antenna, the so-called phase center, changes with respect to the direction and frequency of the incoming signal. Because of that, in data processing, the so-called phase center corrections or PCCs need to be applied. But those values, or the whole antenna model to be more precise, must be previously determined through a special procedure known as antenna calibration. The use of individually calibrated antennas is always the best choice, but it is critical in many fundamental applications like the realization of geodetic reference frames, geodynamics and monitoring, large-scale engineering projects, national course networks, and so on. In a nutshell, my PhD research goals can be summarized in the development of a new calibration system, contributing calibration data and results to the GNSS community, further development of the Croatian positioning system, and enhancing GNSS positioning in general. The system I've developed through my PhD is based on the concept of absolute calibration, whereby the antenna model is determined fully independently on any other reference antenna. The state-of-the-art approach by using a robot raises this topic to a much more interesting level, as a little bit of robotics is also included. The beauty of the robot is that it enables precise spatial rotations of the calibrated antenna so that the full antenna hemisphere can be homogeneously sampled as it is given on the right plot here on the slide. And it is very important as it leads to much more accurate antenna models. A typical calibration setup is given on the slide. The reference and test antennas form a short baseline approximately 5 meters long, which is again a very important property in later data processing. Of course, it is much more interesting to see a video of the calibration and of the robot in action. In total, 2088 different antenna orientations are defined, and with 2.5 seconds stationary at every single one of them, a full calibration lasts approximately 2 hours. Under the hood, software-wise, the system is run by 3 main modules: the main antenna calibration module, the time synchronization module, and in post-processing, the PCC modeling or estimation module. And the software of the system I have custom built in the Python programming environment. As I previously mentioned, the result of a calibration is the PCC model for the entire antenna hemisphere, and given one such example, a visualization in 2D as a polar plot and in 3D can be made. Currently, the system can provide results only for GPS L1 and L2 frequencies. Our repeatability analysis showed that sub-millimeter to millimeter repeatability has been achieved, but most important, by comparison with independent calibration results obtained by the company Geo++ in Germany, the well-known and IGS-approved calibration institution, the accuracy of antenna calibrations for both frequencies has been determined to be sub-millimeter, 0.4 and 0.5 millimeters. That is by itself a very excellent achievement. Furthermore, a short baseline test showed that antenna calibrations with a developed system leads to approximately a threefold increase in baseline accuracy when compared to IGS-type mean antenna models. Also, a GNSS network, medium-scale GNSS network has been tested, and the developed system and individual antenna models resulted in a significant increase in global network accuracy. Finally, to sum up my talk, based on the research results, it is concluded that all research hypotheses are accepted. The developed antenna calibration system is unique in Croatia and Southeast Europe and one of only a few in the world. Furthermore, the calibration system is operational for GPS L1 and L2 frequencies, and my results confirm it to be meaningful in practical applications, thus leading to enhanced GNSS, that is GPS positioning. Future research and developments will primarily be focused on expanding the system to incorporate multiple frequencies and all other global navigation satellite systems, primarily the European Union's Galileo system. That will be a priority. And that is all from me. I really hope you found this topic interesting, and if you have any questions, please do not hesitate to ask. Thank you very much.
Thank you, Antonio. I have one question. You mentioned a Geo++. So can you describe a little bit more? What's the difference between your research and the developments?
The company Geo++ is definitely a standard when antenna calibrations are considered. That company with the operation with the Institute of Hanover, University of Hanover, they were the ones who developed the first robotic antenna calibration system in the beginning of the 2000s, and they are approved by the IGS to provide officially acceptable antenna calibrations. Our calibration system is this is the first research in this field, and as I mentioned, we are only dealing with GPS dual frequency calibrations now, and our system has to be, of course, must be expanded to incorporate all other global navigation satellite systems. So,
but it was totally made by your.
Yes, it is. The calibration system developed for my PhD is completely developed from scratch at our faculty. We share some basic concepts like absolute calibration because this is the standard today. Everything else is not interesting because lower accuracies are achieved. But our system is a fully new system. We have several modeling differences based with respect to Geo++, and that's all.
Mm-hmm. Thank you.
I would just like to add, so because Geo++ is the standard when calibrations are considered, they were the ones we reached out to, and they calibrated our antenna so we could compare based on their results to conclude what our calibration accuracy is. So this was the approach because, as I said, they are the #1 in the world when calibrations are considered.
Okay,
I have one quick question. Huh? I guess you base it on the exactly same principle as the G++ calibration in order to mitigate or eliminate the multipass. Is your robot cheaper than the one from Hanover?
That is a very that's a difficult question. I don't know, because the robot that the Geo++ and Hanover are using, that is a custom-made robot that they made, and they calibrated it by itself. And our robot that I have utilized within our system is a commercially robot from Mitsubishi, a commercially bought robot. So that's totally different, I would say. Our robot is also, we have, through my PhD, we have also calibrated the robot to confirm that the rotation accuracy satisfies our needs. But when the robot is considered, that's the difference. They have a custom-made robot.
Are you planning to license or sell your solution?
I would not say that we plan to sell it, but our goal is, after we incorporate all other global navigation satellite systems, our plan is to certify the robot, firstly on the Croatian level. Then we will definitely think about international, that is through the international GNSS service. But for now, this is the point that we are. And methodologically wise, we have several differences when Geo++ and Hanover are considered. Their calibration, so I don't want it to be too technical, but their calibrations are on the raw, in Geo++ on the raw phase measurements, in Hanover on the single differences. We have the mathematical model based on the triple difference carrier phase. So there are many differences, but in generally the robotic principle has to be, because that is the standard today. That is definitely the best approach that there is.
Thank you.
Thank you.
Thank you.
Paul?
Yes, I have one question. Thanks for this presentation. What do you think? Is it better to have a very good antenna, so I will say the tracking antenna, for example, with a standard ATX calibration, or better to have, I would say, low-cost antenna, which is well calibrated with your system, for example?
So I would say it is much better to have a high-end antenna because the signal reception properties of the antenna is not the only property of the antenna. There is multipath mitigation and many other properties that high-end antennas are much better at than low-cost antennas. Calibration is in both sorts, so in high-end and low-cost antennas, calibration is definitely a must go when high accuracy positioning is required. But personally, I think that high-end antennas and standard Antix files is a better choice than low-cost antennas, and by that I really mean low-cost antennas, than an individual calibration, mainly because of other reception properties, that is, for example, multipath and so on, just as a one difference.
And regarding the improvement you measured in RTK, I think when post-processing, I don't know, you see such improvement also with, I would say, good antennas like chockering or something like that?
Can you please repeat the question? I did not fully understand.
Yes, you show some improvement from 1 centimeter to 3 millimeters with short-long base measurement. Did you measure such improvement with each type of antenna, or was it specifically with low-cost antenna, or also with expensive antenna?
Our test with a short baseline, I would say that was with a mid-range antenna. That was a Trimble Zephyr 2 geodetic antenna. I would place, so that is a reference grade station antenna. So I would place it at a mid-range. It's not a choke ring or, so that was the result with our antennas. Okay, so I think.
Okay.
Thank you very much.
Thank you, Antonio.
Thank you very much.
You have a lot of questions. Okay, thank you again.
Thank you much.
Yeah, and we move to the next presenter from Polytechnical University of Madrid, and another teamwork. It's Juan Portela and his team. Juan, can you open your mic?
Yeah, good afternoon.
Yes, good. We can hear you. So are you ready?
Yes, whenever you want. Yes, please enable the content. Thank you. So thank you for the introduction and good afternoon, everyone. I'm Juan Portela, a PhD candidate at the Technical University of Madrid, and today I'm presenting part of my research conducted with my thesis advisors on using geodetic data, InSAR and GNSS to assess seismic hazard in El Salvador. So earthquakes threaten both human lives and infrastructure. In the last century, they have caused over 2.3 million casualties, with some events resulting in tens of thousands of deaths that you can see there in the graph. El Salvador has experienced destructive earthquakes in the past, making it crucial to understand how they are generated. So earthquakes originate when stress is released in weak areas of the earth crust. This is the faults. When they occur, they also deform the surface, and we can observe these motions using geodetic techniques such as GNSS. You can see there an earthquake in 2011 in Japan and the response of the GNSS. But how does this stress build up? So if we install a GNSS station on solid ground, we can observe how its position changes over time and calculate the velocity at which the surface is moving at that point. If we install a station on the other side of an active fault, we would observe a different interseismic velocity. So if, as in the previous case, the two sides of the fault just slide past each other, so we say they creep, no stress builds up on the fault, and thus no earthquakes will be generated. If we project the velocities onto a profile orthogonal to the fault, we can observe a gap in such case. You can see there on the right, like a gap between the two sides of the fault. But on the other hand, if the fault is locked, the stress would accumulate along its plane and eventually breaks, resulting in an earthquake. In those cases, the velocity profile would appear as shown on the right. So there's no gap, there is more like a gradual change. This is the most dangerous case, of course. So understanding the kinematics of the faults is critical for assessing seismic hazard. The key parameters for this are the depth and degree of locking in the fault. So this can go from creep to completely locked, as well as the fault slip rate, which is the deficit of motion accumulated on the fault that we can see, for example, in the profile. But what happens if we only have one station at each side of the fault? It is difficult to solve for the stress accumulation. However, if we add satellite radar interferometry, we can obtain a better spatial coverage. InSAR provides potentially continuous deformation measurements, but in one dimension, the satellite line of sight, instead of the 3D of the GNSS, and lower precision. So going back to El Salvador, the country is located in a complex tectonic area where the Cocos Plate subducts under the Caribbean Plate. The country of El Salvador is crossed by faults and volcanoes that separate the Caribbean Plate from the volcanic forearc that escapes 13 millimeters per year towards the west. This is causing stress in the fault. We processed 22 years of GNSS raw observations from 171 stations across the Caribbean and the Americas, but with the main focus on El Salvador. And we also use the radar satellite images of the Japanese ALOS mission, covering El Salvador in both ascending and descending orbits. So we start by computing the GNSS velocities, including our own campaigns, and we use them for computing a pole for the Caribbean Plate. Then we compute the loss velocities from ALOS, and we use both datasets to derive fault kinematics from simple models, and then from more complex block models by inverting the data. We obtain the kinematics. So the motion of a tectonic plate can be characterized by its rotation with respect to a pole, the Euler pole, with a certain angular velocity. We invert our horizontal GNSS velocities in the Caribbean and obtain a new Euler pole for the plate, which will be useful for any future geodetic application in the region. The horizontal GNSS velocities in El Salvador, with respect to this Caribbean pole, show the 13 millimeters per year escape of the forearc south of the main faults. So the north of those faults, the plate is more stable. And now we will have a look, for example, at that profile shown in green. So this profile that is orthogonal to the faults, we can fit a simple dislocation model to obtain the slip rate, which is about 12.4 millimeters per year, and the locking depth about 9 kilometers, of a virtual fault in the middle. But we lack resolution to solve for small mapped faults like AF and GF that you see there. So we don't know how they are behaving. Here now you can see the mean InSAR velocity in ascending line of sight geometry. So the satellite is observing from the left to the right, as in the arrows you can see. So the south of the country moves towards the satellite, while the north moves away from the satellite. This is in good agreement with the GNSS results, and we will have a look now at that profile. So you can see that if it were only for the GNSS data, the green dots, we wouldn't be able to reach any conclusions. However, thanks to the InSAR data, the blue dots, we have more information near the fault, and it allows us to accurately fit a dislocation model and invert for the slip rate and locking depth. So you can see here our main findings summarized in this figure, with the numbers in red indicating the new fault slip rates we have determined. And the results also shed some light on the transmission of the deformation in the surrounding countries, Guatemala and Nicaragua. And this data is crucial for new seismic hazard estimation. We also built more complex kinematic models in El Salvador. These models involve rigid blocks that rotate. As you can see, there are 3. And they generate stress along their boundaries, the faults. By inverting the GNSS and InSAR velocities, we obtain new kinematic parameters, but this part is still awaiting publication. So as part of my PhD, we are also conducting a similar research in the Eastern Betics, which are in southeastern Spain, where the tectonic deformation is dominated by the convergence of the African and Eurasian plates. Together with my thesis advisors, who also deserve credit for this work, and other colleagues, we continue observing GNSS campaigns in the area. So most of this presentation is based on the results of a paper we published this year about tectonic deformation in El Salvador. You can see the reference in the slide. And of course, I want to thank you all for your attention, and please feel free to ask any questions. Thank you.
Thank you, Juan. Jury, do you have questions? Everybody a bit tired already, maybe. Okay, InSAR technology is something new. Maybe that's why there's maybe not so many questions. And so, okay, thank you, Juan, for the presentation. And we go to the next presenter, Kamil Choromanski from Warsaw University of Technology from Poland. So, Kamil, yes. We can hear you well. And are you ready?
Yes, I am ready. Thank you very much. Okay, so hello everybody. My name is Kamil Choromanski. I'm from Warsaw University of Technology in Poland. And today I would like to introduce you to an automatic mapping solution for Mars surface I've been working on during a larger research project related to this planet. But first, let me do a short introduction of the problem itself. So mainly processes related to wind, named aeolian processes, are playing a dominant role on present-day Mars, and bed forms created due to such processes cover almost entire area of a planet. Also, mapping of these forms is crucial both for understanding planet's climate history and planning of future missions. Actually, we have a lot of ground and spaceborne data from Mars, so we can map such forms, but manual approach is very, very slow. It's too slow to make it work for global analysis. However, in order to make it the most for the further research, such mapping should be done with very high precision. So the question is how to achieve this goal both on large scale and in short time. So my basic idea was to use a convolutional deep learning model because such models are characterized by very good results on raster data. which is basically what we have here. But to achieve highest possible quality, I decided to create a system that is capable of integrating multiple data sources, both representing global context, like data from orbiters, and local, like images from Martian rovers. And on the diagram, you can see here, the idea is visualized. So basically, the task was to use both rover data, images in this case, and orbital data, namely orbital imagery and digital terrain model in one neural network-based system. Of course, not every type of this data is available on the entire surface of Mars. So in this approach, it is assumed to test how the system works only with a subset of the data. As a research area, Meridiani Planon was chosen due to the fact that it's a very interesting area from Aeolian point of view, heavily populated by these forms. Also, Opportunity rover was operating there, so it was possible to integrate data from this rover, and it have very good coverage of orbital data. The main area of interest was located in 100-meter buffer of Opportunity traverse, which you can see on the right in the yellow. In this area, all analyzed data types were available, and it's nearly 40 kilometers long, and various Aeolian relief types are represented there. And now I will try to introduce you to the data types available on Mars. The first and the most important type of data is orbital imagery. High-res sensor is imaging sensor with the highest resolution available on Mars. Spatial resolution is about 30 centimeters per pixels, which is actually quite impressive also for Earth data. The red band was used for these experiments because it's the widest band that is collected by this instrument, because obviously planet is red, so the most information is there. The second data source was elevation data. It's also from high-rise. It takes images with high spatial overlap, so it was possible to extract elevation information with use of photogrammetric methods. And elevation model represents the range of data which is not fixed, which is not a good situation for neural network models. So also the derivative models were created to get fixed range. And the last but not least type for integrated data were images from Curiosity rover, specifically from NavCam camera, that had represented local context in the system. The Aeolian forms can be seen very well on this rover with very high precision, what can be seen on the images. So, with help of specialists in the area of Martian geomorphology, we created training dataset covering most important classes related to wind processes. So, ripple fields on the far right of the image, ripples on bedrock in the middle of the image, and sand gravel covers on the left. Of course, a created dataset was then split on train and test subsets to assess the quality. As you can see here, the distinction between classes are really subtle, and it was a demanding task even from professionals to properly map these classes. So it is also a complicated task in terms of automatic mapping. Now when you know a bit about input data available on Mars, it's time to come back for a moment to the basic idea. So combining global and local context. So main question of my research was how to integrate these two completely different data types into one system. And in simple terms, the solution was to transform everything to one spatial domain and prepare such neural network architecture that will take advantage of both data types. So the first step in this process must be data integration. So we started from opportunity images that were processed into panoramas to get combined information about each point where photos were taken. And this demanded also, of course, the analysis of metadata and the reprojection and stitching of images producing one panorama. In second step, pre-trained feature extraction network, well-known network named Places CNN, was used to extract features from each panorama to the form of 1D vector, and then the numbers from the vector were interpolated onto spatial domain of orbital imagery. The interpolation method was based on popular inverse distance weighting method, so the base assumption was that near panoramas are more important than those far apart. And now, going to the neural network architecture, main assumption was that orbital information is more important than rover interpolated data, and also it was important to get the most from the rover features. So there are two separated encoders that combines these features in two ways, combining rover features in separate process. And now we can see a list of the experiments. As you can see, all experiments use high-res imagery, and half of the experiments used also rover data. During the experiment, I also tested which types of elevation model derivative will be better, topographic and ruggedness position indices or longitudinal and cross-sectional curvatures. And now we'll see the most exciting part, for me at least. So the results, what is the most important outcome here is the fact that integration of rover data indeed affected in better quality of the results. And in combination with TPI and TRI models, the model achieved nearly 96% of accuracy. And one can think that the difference is not that big and not worth additional work, but we can see on the visual examples here that additional use of rover data resulted in mapping much more closer to experts' manual mapping, which is in black on the image here. And the results were similar in simple areas, but on more complicated areas and on the borders, the results from fused approach was much better. So now going to the conclusions, the main finding of my work is that the use of additional data sources has significantly improved the results of automatic mapping of aeolian forms on Mars, and such results proved to be good enough for aeolian processes experts for their work. But it's important to say that such integration was not straightforward, and sometimes simple equals better. Thank you very much for attention, and I will be happy to answer any questions.
Thank you. Thank you. Very interesting topic. I'm not an expert on such kind of measuring. Maybe Anne-Marie has some question, or other jury members. So it seems no questions again. Okay, so thank you, Kamil, for your presentation.
Thank you very much.
Maybe just one question, sorry.
Oh, yes, we have.
Yes. Which accuracy do you think you have? Because you mentioned 95%, but is it meter, 10 meters accuracy, centimeters? So I don't have an idea.
Okay, so it's an accuracy of the model. So how accurate the aeolian forms were segmented. So it's not the like geodesic accuracy.
The model.
Is the model
okay.
Yeah, evaluation.
Okay, understand better. And do you have an idea about the accuracy of the model at the end? Did you have?
You mean the geodesic accuracy, or?
Yes, in terms of geodesic accuracy.
Well, basically it is limited by the input data. So the accuracy or the precision of the main product here, which is orbital data, is 30 centimeters.
Okay, thank you.
Thank you very much.
Mm-hmm. Thank you again. Yeah.
Thank you.
Okay, we go to the next presenter, and she's Roca Mora, and she's from University Cádiz and Spanish National Research Council. So, Roca, are you with us?
Hi, can you hear me?
Yes, very good.
Perfect.
Yes, so if you're ready, we can start.
Yeah, we can start. So good afternoon, everyone. So I'm going to present some part of my PhD that is called Seagrass and Invasive Algae Mapping, an Earth Observation Approach to Support European Blue Carbon Strategies. This topic is a bit different, so I'm going to do an introduction for you to understand what are we mapping. So I'm a third-year PhD student between the University of Cádiz and the National Spanish Research Council. I'm an oceanographer, but I also have a background in GIS, data science, and also in coastal management. So I'm in this department of Earth observation in the south of Spain. And first of all, just for you to have a picture, I would like to introduce what are seagrasses. Seagrasses are terrestrial plants that went back into the ocean maybe a million years ago. So they stayed in the substrate. And so they are marine plants with flowers, roots, and seeds. And so in this context, why are they important and why is Europe so interested on it? Because they are natural carbon sinks. They are taking out CO2 from the atmosphere back into the soil, and they sequester 35% faster than forests. So they are sequestering 42% of this carbon, what is called blue carbon. If we go to the European context, a third of these seagrasses is lost in the last century, and especially in the Mediterranean, we have this species, Posidonia oceanica, that is the one with highest speed. sequestering this carbon, and is destroyed mainly through recreational boating with the anchors. But not only these threats, we have now a new threat due to this invasive algae species that entered 10 years ago, and this is the favorability expansion map. As you can see, the Mediterranean is a hotspot, and it's expanding very, very fast. So this is one of the main threats. So as you can see in the graph, this is the workflow, and they are very important because they keep this carbon in the long term. They cannot be burned, but they are mitigating climate change, and if we protect them, we are avoiding emissions of the already sequestered carbon in the soil. So Europe is trying to quantify now this blue carbon from seagrasses in every European member state, and they have to map a large area, all Europe, with expensive field techniques, and the method is not standardized. So we developed a proposal that is an Earth observation approach for the European members to have a tool to report this carbon from space. So I'm gonna present two works from my PhD. The first one, the detection of this macroalgae through different sensors from the field to the space, and the second one to map these seagrasses and to quantify this carbon on the soil of this seagrass. So this is the first work from the invasive species. We use Landsat 8, Sentinel-2, a drone with RTK, and the field radiometer in situ, so we could have the spectral signatures of the algae in different states of the beach and underwater, and we went up to 5-meter depth. As you can see, this is the result from the radiometer, so we could characterize the spectral signature of the algae, so we could know how to identify it from the drone and from the satellite. And in the next slide, you will see the windows of each sensor. Here you can see, here was the peak of the algae. So with Sentinel-2 and the drone, we could detect it with a multispectral camera with accuracies of 91% at 8 meter and Sentinel-2 with 10-meter pixel, but not with Landsat 8, only presence, absence. So in this sense, this was the first work. The second work was detecting this seagrass to extrapolate this carbon from the European Commission. So we did this work in the Balearic Islands using Google Earth Engine because we needed a lot of computation. So that was the only way of having that computation on the cloud. And this is the workflow. First of all, we used a lot of Sentinel-2 images at 10-meter resolution, so we could have a percentile of the images and removing a lot of noise from this composite, training and validation data design, and then we classified and we extrapolated the carbon of the seagrasses. In the first step, we used a 7-year window, so we could have the best pixel and the best percentile of the composition, removing all the noise. And these are the 3 classes that we use: the seagrass detection, the sand, and the optically deep waters that are super deep or in the shadow that we cannot detect. So for the classification, we used a random forest classification with a probabilistic approach. And this is the map of the seagrass, how we detected with a 92.5% of overall accuracy across all the depth from 0 to 30 meters depth. So here are the 4 products that we got: the composite of all these images from the satellite, the bathymetry, the seagrass, and the probabilistic uncertainty related to the extent. And dependent on depth, as we had the bathymetry, we could extrapolate from in situ information the carbon fixation and sequestration rates having these maps. So in conclusion, we could quantify the invasive algae species from the first work. The cloud computing to process all these images was super crucial to get an accurate map of seagrass maps. And the development method is a promising tool for the member states to report this carbon at a regional scale. For the next steps, we would like to include the hyperspectral satellite data for the seagrass. And now I'm working in the European Commission as part of my PhD to blend numerical modeling and carbon estimation to check if there are regional differences across the Mediterranean Sea. So these are next steps. Thank you very much for your attention. Here you have my contact if someone is interested in this topic. And thank you.
Yeah, Thank you, Maroka. Very good presentation and a good topic. Okay. Do we have a questions? Kumar? This could be also very useful in Latvia. We also have problems with invasive algae in the future in Baltic Sea.
Yeah, well, maybe this one goes up there in 10 years.
Okay, thank you. It seems no questions at the moment.
Thank you so much.
Okay, so we are at the last presenter today, and she's Natasha Maliansky Andreevska. I think I was clear.
Yes.
And she's from Kirlik and Metadeos University from the Republic of North Macedonia. Okay, Natasha, are you ready?
Yes, I am. Good afternoon. My name is Natasha Malianska Andreevska. I am a member of the chair of Geodesy at the Faculty of Civil Engineering in Skopje, North Macedonia. And today I am pleased to present my research on assessment of solar photovoltaic potential of building rooftops based on multi-criteria spatial analysis. The presentation is structured into several sections. I will start with a brief introduction to the problem, then I will present the established methodology through the research case study, and finally I will share the research results and conclusions, and I will outline the next steps. According to one report from the United Nations, even though cities cover only 3% of the Earth's surface, their contribution is up to 80% of global energy consumption and 75% of greenhouse gas emissions. Meeting electricity demand sustainably without negative impact on the environment or the economy is a complex challenge, and one of the potential solutions is to focus on the usage of renewable energy sources, such as the solar energy, for electricity production. In urban areas where solar energy is one of the more accessible renewable energy sources, building rooftops are considered as one of the most suitable location for installing a solar photovoltaic systems, but not all roof surfaces are equally suitable. So to identify the suitable roof surfaces and to estimate their solar photovoltaic potential, the integration of different spatial data from different sources such as LiDAR data, cadastral data, orthophoto images, etc., can be a good foundation for complex analysis. So the goal of the research was to establish a methodology for assessing the solar photovoltaic potential of building footprints based on the available spatial data in Republic of North Macedonia using spatial modeling and GIS technology. The research case study took part of an urban area in the city of Strumica. The research area covers 38 hectares with different buildings, and the main data source was a LiDAR point cloud provided by the Agency for Real Estate Cadastre of North Macedonia. As we can see on the screen, the established methodology consists of many steps, but in general, the process could be divided into two main parts: extraction of building footprints and modeling solar photovoltaic potential of building rooftops. In order to extract the building footprints, the LiDAR point cloud data was classified in four main classes: noise, ground, non-ground, and building points. The most important are the points from the class buildings, because these points are representing the building roof surfaces. So the next step is processing the points from class buildings, and the processes are generation of building raster model, conversion of raster model of building footprints into vector format, and building footprints regularization. all in order to extract the building footprints given on the right image. The next part of the process is focusing on the modeling of solar photovoltaic potential building rooftops, and all of the following steps are based on the digital surface model generated from the LiDAR point cloud data from the points from from the first return. Then the digital model of rooftops slope and aspects were created, limited only to the boundary of the extracted building footprints. And finally, the most important raster model is solar radiation model. It is a sophisticated model that considers the sun's position through the year and day, as well as obstacles like trees or buildings and the slope and orientation of the roof surface. The resulting model has a pixel value representing the amount of solar radiation for every roof surface. The next step is in the identification of suitable roof surfaces. So as suitable roof surfaces are considered ones that meet the criteria given on the screen, and the last step is only focusing on the roof surfaces that from these steps are considered as suitable. So the final step is assessing of solar photovoltaic potential of building roof surfaces by estimating the solar radiation per building and the potential for production of electricity for electric energy per building and for all the analyzed research area. So the results from the all identified buildings, 62% are considered as suitable for installation of solar photovoltaic systems. As conclusion, we can say that the combination of LiDAR data and spatial modeling enables sophisticated analysis and efficient identification of optimal location for installation of solar photovoltaic systems. And as next research steps, we are focusing on applying the methodology to a larger area on a city, region, or country level, establishing a web-based platform for solar cadastre, and implementing BIM as data source for assessing the solar photovoltaic potential of building rooftops. Thank you for your attention. I hope I managed to be clear in this short time and to present this, I can say, a long research.
Okay, thank you, Natasha. You were clear. It's more practical topic you have, and I have a question that does your results or authorities are interested on your results to involve somehow in a practical life?
Yes, the authorities like the government or the municipalities are interested. So I think that this will be a good collaboration also with the institution, maybe for this platform, so for solar cadastre, etc. We will see. Yes, in the next steps, research steps.
Mm-hmm. Some other questions from the jury? Okay, seems not. Okay, thank you, Natasha.
Thank you.
I would like to thank all participants who joined this evening. We finished with presentations. A special thanks to all presenters. Keep on studying, keep on researching, keep on doing good things. Okay, so thank you everybody once again, and see you on awarding ceremony in Intergeo. And for the finalists, tomorrow I will write you some emails with some results, and we will inform you for the next steps. Okay, bye-bye. See you next year.
Thank you, everyone. See you.
Thank you. Bye.
Thank you. Goodbye.
Thank you.
Goodbye.
Goodbye.
Thank you. Bye.